Okay, so before we really get started on talking about Gauss's law, I want to go over a couple pretty important things that we need to know before we really start talking about Gauss's law. And the first thing is going to be Maxwell's equations. And the second thing is going to be geometry. So first thing, second thing. And we're going to deal with these two things because all of the previous chapter on Coulomb's law, we really were just using Coulomb's law, which says for a point charge, if you have a point charge that looks like this, it has an electric field that points out like this. I mean, it's in 3 dimensions, so you have to sort of use your imagination. It starts at the positive charge, right? And these are field lines. If you want to draw them as vectors, these would be field lines, which means I have to start at the charge. If you want to draw them as vectors, you need to make sure they're bigger near the charge and smaller as you go farther away. And we basically just said, you know, hey, we know this is the field. This is what it looks like. It drops off as inverse squared. So we know that E is equal to KQ over R squared. And then you can make this a vector. And then you can make this a differential, and then you can add up a bunch of charges if you have like something like a line, and there's all this integral stuff, okay? And it was very simple conceptually, right? You just know that you have a charge, it has an electric field that looks a particular way, and you can just add up all those electric fields at a point. Gauss's law is much simpler mathematically. It doesn't include a lot of integrals, even though it looks like it has an integral, and I'll show you that in a minute. But it does include a fair amount of figuring out shapes, because this is going to be using sort of a 3-dimensional vector calculus to get a much simpler way of solving these things, which in concept is much more complicated, but the math is simple once you get the concept. So before we even get started with any of that, though, I'd really like to talk about Maxwell's equations. And Maxwell's equations can be written in an integral or differential form. The Gauss's law as we know it, well, I'm going to write them in differential form, and it's a more advanced way of looking at it, but I'll explain why we're doing that in a minute. So here is Gauss's law in differential form, right? And then that's Gauss's law. This is sort of Gauss's law for magnetic fields. And we'll talk about what that means in a minute. And then we have, so these are both divergence, right? And we'll talk about what divergence means. Then we end up with the curl of electric field. So the curl of electric field gives us something that looks like this, where this is and then we have the curl of the magnetic field, which gives us something that looks like this. That's J. So here you have these things called divergence and curl. And just for a side note, Maxwell's equations, they all have names, and we'll go over them in a little bit. But this is Gauss's law, which we're going to be talking about in this chapter. This is Gauss's law for magnetic fields, which we only briefly mentioned, but it's important because it tells us that you can't break north and south apart on magnets. That's called no magnetic monopoles. This is Faraday's law, and we'll talk about that when we get to induction. And this is the Ampere-Maxwell law. We'll start with just this part right here, and then eventually we'll get to the whole thing. But the key here is we're going to be starting with Gauss's law, and I just want to go a little bit over what divergence and curl means. So when we talk about this, you know, positive charge that has these electric field lines that go out like this, these field lines are diverging. And what that means is the vector field is generally going outward, okay? If you have a negative charge, you would have a negative divergence, because if you have a negative charge, you have a negative field line, so they point towards your charge, okay? And all charges, positive and negative, all the field lines point away from the positive charges and towards the negative charge. But you can have a positive charge by itself, and you can have a negative charge by itself, meaning the divergence of the field is sort of the outwardness or inwardness. Okay, so you can think of these things, if you're thinking of it in terms of heat, like sources and sinks. So the divergence here, this is this del dot whatever the field is, okay? And divergence is sort of a measure of how much the field is going out or in. If you have something like a surface, right, the divergence of this field, you can see at each of these points, the field is going out, right? Same thing here. If you see at each of these points, the field is going in. If you have a positive and a negative together, then your field looks a little bit different. So let's draw the field. We'll use yellow in this, or gray, okay? So then in that case, you can see it goes from positive to negative. Oops. Like this. This is what your field looks like. And so if you drew a surface around both of these, you can see every time you have a field line that goes out, it also comes back in. So here the divergence would be 0, okay? Because everything that goes out comes back in. Same over here. If it goes out, it comes back in. So they cancel out, okay? And this is very fuzzy, but I'm just sort of getting you a general idea. So that's what divergence means. Curl, you'll notice as we get into later things, we can have field lines like for magnets that end up being complete circles. So if divergence measures the spread outiness, right? So you can have sources and sinks, you can start and end at locations. Circles don't start and end at a particular location. So if you have a field line that looks like this, right? You can see the divergence, because magnetic field lines always are circles. That's why the divergence is 0 for magnetic fields. So for these guys down here, this is the curl, and this measures sort of the curliness of field lines. So if you have field lines that look like this, or field lines that look like this, right, then that's where these come in. So generally, we have these Maxwell's equations, and the one we're going to start to focus on is here. Now, the other way to write this is as an integral, where you have E dot dA, and I can show you how you go back and forth between these, right? But it's not necessarily that important, but just the key here is Gauss's law can be written in these two ways. This is the way that we're going to deal with it in this class, and we'll go over the details of that later in the class. The second thing we wanted to deal with is geometry, and the reason we want to deal with geometry is this whole section has to do with a Gaussian surface, and that's like an imaginary thing. Well, it's a thing we make up to make the math easier, but what it really means is it's a three-dimensional shape that encloses things. So the Gaussian surface usually ends up being a sphere or a cylinder or some sort of box. So the sphere, let's say we have a sphere. Here's a drawing of a sphere. We have cylinders. They look something like this. And then a box would look something like this. Not the best artist, but you get the idea, okay? So if we call this length L, this has a radius R, and this has a radius R. We want to just review the surface area and the volume of these things, because I find people tend to be rusty on these. So the volume of a sphere, volume sphere is, well, let's just make a circle there. is 4/3 pi r cubed. The great way to know if you're dealing with a volume of our surface area is there should be 3 dimensions for the volume, right? That makes sense. And then the surface area is going to be 4 pi r squared. Fun fact, this is the derivative of that. And you can think about why that's the case if you want to. For the cylinder, the volume of the cylinder, that's going to be pi r squared times L, meaning you're going to get pi r squared, that's that, right, times your height, which is basically just base times height, so times L. Okay, it gets a little bit more complicated when you do the surface area of the cylinder. That's going to be these surfaces, right? Those are pi r squared, but there's 2 of them, so you'd say 2 times pi r squared. But you also have this area here, and the way that you calculate that is you want to say, okay, well, we have base times height, okay? So that's going to give us, we have the top and bottom here. So we just need to add on plus 2 pi r, that's the base, right? That's the length of a circle, times L. So when you write this all out, the surface area of your cylinder is going to be 2 pi r squared plus 2 pi r L. And we're going to use parts of this depending on what the problem is, okay? But it's important to sort of know that. For a box, the volume's easy. The volume is going to be L cubed. Okay, once again, here you're looking for 3 dimensions. So this is obviously 3 dimensions. This is obviously 3 dimensions. Slightly less obvious is this times this gives you sort of a cube of sorts, okay? But there's 3 length variables, okay? For the surface area of the cube, you once again have 6 sides times L squared, which is L squared is just 1 surface, and we're assuming this is a cube, but it doesn't have to be a cube, in which case you'd have to calculate each side individually, okay? So just generally, we have volume for a sphere and surface area for a sphere. We have volume, volume for a sphere, surface area for a sphere. Volume for a cylinder, surface area for a cylinder. Volume for a cube, surface area for a cube. But the key thing is being able to figure this out in your head and visualize what each thing is. So this brings us to chapter 22, which is all about Gauss's law. And we're going to start with something that we call flux. And we're going to deal with all of this geometry. The whole point of Gauss's law is to not do integrals, even though the definition of Gauss's law is this double integral with a circle around it, which we call a surface integral. The way that we want to set it up is to use symmetry to our advantage so that we're never actually doing an integral except for, geometrically. But we're not actually calculating trig or use substitutions. And so in that way, it's much nicer than the previous chapter, but it also has a little bit more of a buy-in on the concepts. So I guess buckle your seatbelts. This is always a fun chapter, and work on your spatial skills. All right, so here's sort of our outline for this second chapter. We have charge and electric flux, okay? So we already know a lot about charge. What kinds of charge can we have? Yes, but what signs? Positive and negative, right? There's 2 kinds of materials we've talked about that contain charge. What are they called? Conductors and insulators. What's the difference between the conductors and the insulators?
The signs or the electrons can move freely.
Yeah, in a conductor, the charges can move around freely, right? In an insulator, they can move, but they're usually stuck to the opposite charge. So there's some polarization, meaning there's some, one side's more positive than the other, okay? But it's not as pronounced as in a conductor. So remember, an insulator, even a wall, right, as an insulator, you can stick a charged balloon that you rub on your hair to the wall because, right, the wall still has these little dipoles in it that all sort of point towards the balloon, okay? So in a conductor, you can have dramatic charge redistribution. In an insulator, you have more subtle charge redistribution. It's based on this dipole model, okay? The other thing about conductors is, where does the charge hang out if there's extra charge? How does the charge distribute itself if there's no field? Okay, evenly, and where? On the surface. Okay, it's always on the surface. So if you just have a sheet of charge, then you can assume that the charge is fairly uniformly distributed. If you have like a sphere, that means there's only charge on the outside and the inside should be neutral. Okay? And you want to remember, we call this the middle school dance model of charge distribution. Okay? Think of the little charges as all really not wanting to be near each other and definitely not touching each other and trying to get as far away from each other as possible. Okay? So, then we're going to talk about what electric flux is. So we're going to have to define flux. We'll talk about how we calculate it, and that will lead us into Gauss's law, and then we're just going to spend some time on Gauss's law, and then we'll do Gauss's law with conductors. Okay, so